Hello, good evening. Can you hear me okay with the mic? Yeah, it's all good. Well, good evening and a warm welcome to you all. My name is Professor Frances Bowen, and I'm the Pro-Vice Chancellor for Social Sciences here at UEA. It's my very great pleasure to be introducing Professor Will Penny to you tonight. Will was always interested in maths at school, and he developed an early interest in computing, as his dad's company had one of the first personal computers, a Commodore PET. We did have a discussion about whether it was PET or if it was actually a PET, and indeed he's excited to recall it's a PET, which Will could borrow to program computer games. Will went on to study electronic engineering at Nottingham University to find out how computers work. He then studied communication engineering at Imperial College, where he learnt some interesting maths. And he then worked on artificial neural networks project at Brunel University. This was particularly fascinating to Will because this technology could automatically find patterns in data in a way that was inspired by what was then known about how the brain works. This ignited Will's enduring fascination with maths and the brain. Will then worked developing signal processing and pattern recognition methods as a postdoc in the departments of psychiatry at UCL, electrical engineering at Imperial, and information engineering at Oxford. Later work using machine learning methods to classify EEG data opened the door for Will to work in a brain imaging laboratory. Will went on to work for 17 years at the Wellcome Trust Centre for Human Neuroimaging at UCL as a statistician, an imaging neuroscientist, a lecturer, reader, and then professor. He developed statistical methods for analysing brain imaging data based on Bayesian ideas. A major project involved working on the team that developed the dynamic causal modelling method of brain connectivity analysis. Will joined us here at the UEA in 2017 as a professor of psychology and continues his research on brain imaging. Current research interests also include representation learning. That's understanding how the brain develops representations that are optimal for the task at hand. So please join me now in welcoming Professor Will Penny to give his inaugural lecture this evening. Come on up, Will.
Thank you very much. Thanks very much for coming out tonight. And I'm going to start my story in the 90s, the early 90s, when Nirvana were making some great music. Nelson Mandela had just been released in 1990, and the World Wide Web was just being invented by Tim Berners-Lee at CERN. So really, at that time, there was no internet to speak of. So I was working on a project on artificial neural networks, and the goal of that technology was to develop general-purpose pattern recognition devices that could learn from examples rather than be programs. You just give it examples of what you want it to do, and then it should generalize so that it's learned the task properly, so you could properly classify new examples. And this was really because people were so good at recognizing patterns and computers at that time were not at all. The idea was that, well, let's take some inspiration from how we think the brains work. So these general purpose pattern recognition systems are comprised of rather abstract models of neurons, where this neuron here, for example, receives signals from these three in the layer below. It weights their inputs, adds them up, compares the sum to a threshold, and then outputs a signal and sends it to these other neurons. And if you want it to do a particular task, all you do is give it a training set. So that will be some images, for example, that you want to classify, and some labels where you tell the machine what category of image, for example, you're showing it. So I'll just go through a quick example of training this network to classify images as either of dogs or of cats. So here's an image of a dog, and we tell the network that this is a dog. So this would be the dog unit, and this would be the cat unit. And so this is our labeled data. We give it another example, and an example of a cat, another example of a cat, and you would give it typically hundreds of examples. And this is really quite a difficult pattern recognition problem because you see the images are coloured, the cats and dogs are in different poses, different positions. Some images are really sort of close cropped to the face, others are of the animal more generally in its environment. But nevertheless, you can get these neural networks to learn these mappings. And then, of course, you want to be able to present it with a new image of a dog that's not been in the training set, and for it to say, with 95% probability, yes, this is a dog. And with artificial neural networks, we wanted these to be a general purpose pattern recognition system so that it would work with images, but also with speech, and generally any type of data that you would wish to give it. Now, so I started working in this area in the early 90s, and around that time, a few years before, Jeff Hinton had actually rediscovered an algorithm for training these networks. And although people had been working on it before, he sort of reinvented it and popularized it. And at that time, his work appeared in this book, and this was the book that was on all of our desks at that time, the PDP book. And many of you psychologists here will have also had that book on your desk. Do you still have it? I've lost mine. Has anyone still got it? Okay. Yes. Right. Now, one issue about these neural networks, though, is that at the time they didn't actually generalize that well. So we could get some data, we could train them on a data set, but when we gave it new examples, it didn't really work so well. Or it wasn't really clear why it would work and why it didn't work. And then it became apparent that we really needed to be quite careful about the structure of these networks. How many hidden layers they would have, how many hidden units in each hidden layer. And this, the structure of the network really determined how well it could generalize. And so I refer to this as the structure learning problem. And there was no real solution to this. There were a few sort of ad hoc methods that people used that didn't work very well. And also, there was no real theory as to how we should go about solving this problem until David Mackay applied ideas from Bayesian inference. And a decade or so later, he wrote this fantastic book which tells you all about pattern recognition and machine learning, and it's a great book. So the central quantity that David Mackay proposed that we use is called the Bayesian model evidence. And so it's simply the probability of some data given a model. And the best model is the one that has the highest model evidence. So it's conceptually very simple, but in practice, to compute this number, this is a probability, it's just a number. To compute that number was more difficult, and it involves two concepts which I'll just briefly talk you through. The first concept which the Bayesians brought to the table is the notion of a prior distribution. So even before this network is exposed to any data, we actually have some beliefs about what we think these weights are going to be. So these are not going to take on very large or very large positive or very large negative numbers. They're going to be in a certain range, and we know that already. So we may as well use that information and constrain the estimates to that range. And this is captured by the prior distribution over the weights vector. So if there's 100 weights in this network, then W is a vector with 100 elements in. So in the Bayesian framework, we have a prior over the weights. The second concept that we need to think about is the likelihood. this is simply the probability that we get the correct labels given our current estimates of the weights. And in maximum likelihood learning, you would change the weights to maximize the likelihood. Now we have those two concepts, the prior and the likelihood. If we multiply those two numbers and then add them up over all possible settings of the weights vector, we're effectively summing out the effect of the weights, and we end up with the model evidence. And if we then think about the weights vector as a continuous quantity, this sum just turns into an integral. Now, some of you may be pleased to know that this will be the last equation that I present in the talk. I like maths, so I was always going to give you some equations, and this is one of my favourite ones. But there won't be any more in the talk. And in fact, how we can really understand the model evidence is to express it in a slightly different way. And we can rearrange some of the terms in that equation, and I'll just write it out in words here, such that the model evidence equals some terms involving the accuracy of the model, how well it fits the data, and the complexity of the model. And this turns out to be a mathematical generalization of Occam's razor. So William of Ockham is a philosopher who came up with this dictum that if two hypotheses explain the same data, we should prefer the simpler one. And what the model evidence is really a quantification of that. For any model and any data set, we can now compute a number which quantifies how good that model is. So applying this concept to artificial neural networks, where we might want to find, for example, how many hidden units we should have in the network, one can simply compute the log evidence as a function as we slowly increase the number of hidden units. The evidence gets higher and higher up to some maximum here and then falls off. So we now know that we should have 9 networks in order for this network to generalize well. And so in the 90s, I applied this methodology to lots of problems, and actually not just neural network models, but various models in signal processing, which try to, for example, predict the next value in the time series as a function of previous values or previous values of other time series. And it really was both a mathematically very well principled tool, but one that worked very well in practice. And so that really takes us up to the end of the 90s, to 1999. So I looked up on the internet important events of the 20th century and 21st century, 20th century, and 1999, introduction of the euro. So many important things happening in Europe that year, but more importantly, this is a more memorable event. Perhaps a number of you remember where you were when this event happened. Perhaps not. Also in 1999, I was at a neural networks conference in Washington, and there was an amazing talk by a guy called Christian Buchel. And he was talking about neural network models that could be fitted to brain imaging data, which I thought was really exciting. And so I spoke to him, and he told me that he worked with a guy at UCL called Carl Friston, who was working in that area, and so that led me to chase up the possibility of working with him. And so I did. There was a job there, and this led me into the area of neuroscience. So the artificial neural networks that I've described really bear little resemblance to real neuronal systems, to real brains. One of the biggest differences is that in artificial neural nets, there's just a single phase of processing from the sensory input to a decision-making layer at the top here. Whereas in the brain, that's not the case. There are feed-forward and feedback pathways, and we see basically information passing both ways in a sort of iterative process. So I therefore went to work at UCL to study brain connectivity. Now, when people talk about brain connectivity, they could be talking about three different things. So first of all, there's the anatomical structure of the brain. So this is basically what we refer to as white matter. So big bundles of axons that connect one brain region to another brain region. This is the structure of the brain, with only changes on a very, very slow time scale. Then there's functional connectivity. What you would do is, to measure functional connectivity, you measure activity at this point in the brain and at that point, and you simply measure the correlation between those two time series. So looking at instantaneous relationships between activity in different brain regions. The third type of connectivity, we try to infer directed relationships among regions. In other words, is activity here, changes in activity here caused by activity there or by some other region? And this is the sort of neural network model that Carl Friston was working on at UCL, and his model was called dynamic causal modeling. Dynamic and causal because it's actually based on differential equation models of neuronal activity, like, for example, some other mathematical models that had been developed in the field. So with these differential equations, that's good for modeling time series. So I'm going to talk you through this dynamic causal modeling approach as it's applied to MEG data. So an MEG scanner detects very small changes in the magnetic field outside the head, but it's sensitive to neuronal activity in the brain. And it's a non-invasive technique. You can simply, there's no wires here connecting your head to the machine. You simply sit in the machine and put yourself, it's like going to have your hair done. And you just get your brain recorded for a while. And then the idea, of course, we get signals that are related to activity in the brain. And what DCM tries to do is to turn those signals into estimates of activity in different pathways in the brain. So how one brain region communicates with another. So there's like 3 or 4 steps to the DCM, and I'll just go through these. So if someone's in a MEG scanner and you show them an image of something, then this will stimulate activity in, say, the visual cortex. So visual processing actually, in the brain is actually, the visual cortex is at the back of the brain. And these early visual regions would then excite activity in, say, higher level parietal regions. And then these parietal regions would then communicate back to these early visual regions. And there's this recurrent connectivity among brain regions, both feed forward and feedback. Now, on top of that, the activity in each brain region is modeled by another little neural network, where a sort of a stimulating input, a stimulus, would drive activity in stellate cells, which in turn would excite activity in pyramidal cells, then excites inhibitory cells, and then these kill off the activity there. And what we would see is, given a burst of input, say we're looking at an image of a face or something, and we would see activity ramp up and then decay, and then depending on the values of the connections, within a brain region and between brain regions, we would see different amplitudes and different time constants of oscillations. And so you can see that more clearly in this figure here, where at 0 seconds, that's when, for example, an image would be presented to a subject in a MEG scanner. And then we see these evoked responses, and the frequency and amplitude of which is different in each brain region and varies as a function of the connectivity. So this is our neural network model of what's happening in the brain. Now, of course, we can't measure this activity directly, but with a MEG scanner, we can pick up changes in the magnetic field due to activity primarily from the pyramidal cells, just because of the way they're structured. Now, given that we actually have some MEG data, we can then invert this model and use Bayesian inference to estimate some parameters of the model given some real data. And then we can use the same model evidence, Bayesian model evidence measure, to infer what is the best architecture of this neuronal network that best explains the MEG data. And if the subject's performing a different task, how does that change the way that information is routed among these different brain regions? Okay, so I'm going to talk you through just a couple of applications of DCM. It's been used in hundreds of studies. The first application is it's a study of aging by Rosalind Moran, and she scanned about 100 people aged between 20 and 80 in a MEG scanner whilst they listened to auditory tones. This is a very boring experiment. The subjects were just listening to many low tones of exactly the same frequency, and every now and again there would be a high tone, which we refer to as an oddball. It's a sort of a low-frequency, surprising event. So if we now look at the recording from one of the sensors in the MEG scanner, whilst the subject was listening to the standard tone, the low-frequency tone, we see that this blue response evolving in time over 300 milliseconds or so after the tone was presented. Whereas when they're listening to the oddball, we see a rather different recording shown in green here. And then we can just compute the difference of the two, and this is referred to as the mismatch response. Now, this was just a recording from one sensor in the MEG scanner. And in total, there are 300 or so MEG sensors. And because these are arranged in a particular spatial way, it's a bit like radar. So you can then basically use the spatial information in the signal to reconstruct where the activity came from in the brain. So if we do that for the activity at 150 milliseconds after the stimulus, we can see that there's activity in the left and the right auditory pathways in the cortex. Now, Rosalind then fitted a DCM to this data, and using the Bayesian model evidence, she was both able to infer the number of regions and where these regions should be in space, and how they should be connected, and which of these connections are affected by the tone being an oddball versus a standard. And this was the best architecture that she found, where this is right Heschel's gyrus, superior temporal gyrus, inferior frontal gyrus. Now what we got to the stage here where Rosalind has fitted this brain connectivity model to data from 100 subjects, and these subjects are aged from 20 to 80. So then what she did was to try to predict the age of the subject from their connectivity, from their brain connectivity. And she was able to do that rather well. So you can see that there's a reasonably tight agreement between the connectivity-based predictions of age and people's real age. She then looked to see, well, were there any particular connections in the network that were really determining the age? And it turned out that there was one connection in particular, which was the degree to which this bottom-up connection increased when subjects heard the oddball versus the standard tone. And this was much stronger in younger people. And so this is consistent with the idea that younger people have stronger bottom-up signalling. In other words, they pay more attention to the sensory world around them. As we'll see later in the talk, it's hypothesized that top-down connections embody predictions about the world. And in other experiments, we see that older people have stronger top-down connections. In other words, they believe that their predictions are better, probably because they have more experience of the world. But they may not always be right. Okay, so this second experiment I'm going to talk you through is an MRI experiment. So this is a large electromagnet here, and participants go into that magnetic field, and we can tell where in the brain the blood is oxygenated versus deoxygenated, because the molecules have different magnetic properties. And we can produce these exquisite spatial maps of activation in the brain, and I'll show you some in a minute. Now, in this experiment, subjects performed two tasks. The first was a baseline task where a sequence of numbers was shown, and participants were asked just to press a button if you see the number 0. In the more interesting working memory task, again, a sequence of numbers was shown, and so participants were asked to press the button if the number was the same as the number 2 trials before. So let's try that task now, just so you get an idea of the sorts of experiments we get up to in psychology departments. Who's done a psychology experiment before? Okay, well, now's the chance for you all to do one. So I want you to put your hand in the air if the number is the same as the number 2 trials before. Okay, so I'm going to show you 2 trials first. And now you're going to have to make some judgments. Is this the same as the 2 trials before? A lot of people have got their hand up. Do you want to change your mind? Quite a lot of hands up for that one. Quite a lot of hands up for that one. Okay, so the numbers I showed you were as shown here. And so the true answers was same, different, different, same, which I think very few of you got right. So you're not getting paid. Now, it's a really difficult task, and of course you haven't had any practice at all, but you know, when you go into the lab to do the task, you'll practice it, and you'll probably get quite good at it. I personally find this task very difficult, and when I designed this talk, I was trying to both remember how to do the task and ask you about it, and I just don't have the capacity for that. And why it's so difficult is because you have to recall the second to last item, compare it with a new item, and then you sort of have to relabel your stored items. Now, what was the last item should then become the second to last for the next item. And then you need to encode your new item as the last item. So there's all these encoding, storage, and recall processes operating on the same information in the same modality, vision. And so a high possibility that these processes can interfere with each other. Now, Klaus Stephan, who ran this experiment, did it in 40 healthy controls and 40 subjects with schizophrenia. He was then defined working memory activation as basically the activity during the working memory task versus the fMRI activity during the baseline task. And just doing that subtraction, we see that these are the working memory activations in the healthy control group and in the schizophrenia group. So they're largely similar. And here we have activity in parietal cortex and dorsolateral prefrontal cortex. So Klaus then fitted dynamic causal models to these data, a model for each participant. And the Bayesian model evidence showed that working memory affects two pathways, one from the visual cortex to the dorsolateral prefrontal cortex, and one going from there to the parietal cortex. Perhaps this one to do with encoding and this one to do with recall, maintenance. Now, what was especially interesting to me about this data set was that in a few months prior to this project, I'd been working on a Bayesian clustering algorithm. So you basically give it any data, any multivariate data, and it would tell you, is this a homogeneous group of data? In other words, do all these subjects have the same pattern, the same connectivity pattern? Or are there two distinct clusters? Or are there three distinct clusters? Or four? And so we applied that approach to the connectivity patterns from the schizophrenic subjects. And the Bayesian model evidence told us that there were three clusters. Most subjects, 24 out of 40, fell into this cluster here, cluster 2. And then 9 subjects had much stronger connections from dorsolateral prefrontal cortex to parietal cortex. And another 7 subjects had a different pattern yet, which was a stronger connection from visual cortex to DLPFC. Now, Klaus and colleagues had a lot of data on these schizophrenic patients. As you probably know, in schizophrenia there are positive symptoms, hallucinations and delusions, but there are also negative symptoms, which you can see descriptions of here. And it turned out that this blue cluster here, these schizophrenic people had very few negative symptoms, whereas in the green group they had many negative symptoms. And so we could sort of relate the connectivity patterns here to, one can imagine for this cluster 3 where they had lots of negative symptoms. This sort of, the encoding of new stimuli is really, this connection is too strong. You're really interfering with persistent cell firing in this part of the brain, so you're not able to store the data to compare it to, which is not the case in this cluster here with subjects with very few negative symptoms. And so the idea here is that, schizophrenia, please.
Did you record what drugs for schizophrenia? Because you've got a diagnosis of schizophrenia, you're likely to have drugs which can affect
Yes. Absolutely. And that's probably the biggest problem, or one of the biggest problems with clinical research in the area, is that it's very difficult to get subjects who don't have a history of being treated or who are not on medication at the time. But yes, we do have a detailed history of which drugs subjects were on. And now people try to wash out, do studies where people are not on any medication at all, and then you test them and slowly reintroduce different medications. But it's a complicated area. It's one that I'm no expert in, but through collaborations with people like Klaus Stephan, we could try to take what is really a sort of a spectrum disease. Schizophrenia is not a homogeneous process, but there are perhaps many subgroups, and if we can identify these subgroups, then we can perhaps treat them in a different way. So at the end of the talk, I've got a list of references, and we can talk about what medications people are on. Okay, that takes me nicely onto the next decade, which is the royal wedding. I'm sure you remember the royal wedding. Perhaps not where you were, but or maybe you were on holiday in 2010 when there was the volcanic ash cloud, and maybe you were stuck somewhere watching the royal wedding. But also in this decade, deep learning has made a huge impact. So although in the 90s I worked in the sort of artificial neural network field, I sort of thought that this field was not going anywhere. Well, it turns out I was wrong, because in the intervening 15 years or so, people like Jeff Hinton had really pushed the field on and were able to train these very deep networks with hundreds of thousands of parameters on millions of images collected from the internet. And these machines could estimate the coefficients, the weights in the networks, using very powerful computers with graphical processing units and multiple cores. And this led to, for example, DeepMind was formed in 2010, and they were able to, using sort of deep learning approaches, they were able to build a computer that could beat the world Go champion, which was something that we thought would not be seen in our lifetime. And companies like Alexa, which many of you may use, use deep learning for speech recognition. So, this is all very well, I hear you think, but how does the brain work? Well, I'm just going to tell you one theory that's receiving a lot of attention at the moment, and is close to my heart because it's really rooted in Bayesian inference. And this reflects really the hierarchical nature of the brain, where there are multiple hierarchies to do with vision, to do with hearing, and then in the sort of, there are other parts of the brain that are not specific to any modality, so we call them multimodal regions. And if we take a little step-by-step look at this diagram, we can understand a bit more. So here in the periphery, the outside of this circle, are the primary sensory areas. So these are the parts of the brain that get information from the senses first. Now, neurons in layers 1 and 2 only have a very small view of the world. They don't get to see the whole image that I'm seeing of you now. They just get to see just a few degrees like that. And because my eyes and my body move around, we don't really see consistent, persistent activation of cells in these regions. So the activity there changes very fast. If we go up to layers 3 and 4, now the spatial aperture is much bigger, and so through this aperture I can now see faces, I can now see chairs, I can see computers, I can have representations that allow me to say, I can read them and that will tell me what I'm looking at. Am I looking at a face or a chair? Going up to levels 5 and 6 into these multimodal areas, the activations can then persist for seconds, tens of seconds, and yet more. And these are to do with our working memory and our sort of task set, if you like. So I have a sort of temporal map in my brain about what I'm going to say when, what I have said, what I'm going to say. And this is sort of over a temporally extended window. And so with that in mind, I'd like to sort of introduce Dave. I'm just jumping ahead. So what I should say now is that this spatio-temporal structure of the world is reflected in the anatomical connectivity of the brain. So I now introduce you to David Mumford, who's come up with this theory called, a theory of how the brain works called hierarchical predictive coding.
I'm very honored that the committee chose me. I'm delighted to receive this temporary innovations in technology.
Is there a mathematical approach to understanding thought and the brain?
Yes, I believe so. This is not universally accepted by scientists who are studying the brain right now. But my belief is that to really understand it, you first have to make a mathematical model of what thought really is. What in some sense is the structure that we're setting up in our heads and working with in order to understand what's going on and plan our actions. And my belief is that the fundamentals of this kind of thinking are essentially statistical in nature, that we should view what's going on in our heads as statistical inference, that we rely on assembling a huge amount of data about how things work in the world and what we expect to see in the world. And we have to combine that with what's happening to us every day and use that to infer what's really going on beyond the very noisy and incomplete information which we receive about the world around us.
So David Mumford is a mathematician, and he's actually a winner of the Fields Medal, which is their equivalent of the Nobel Prize. Actually, everything else he works on is nothing to do with the brain at all. But this is his theory about the brain. So if we effectively, what he's saying is that these higher level regions place prior constraints onto the lower level regions, which then place prior constraints onto those levels below. And effectively, we have something like a hierarchical Bayesian model. So how does that work in practice? Well, the higher level regions would send predictions down the cortical hierarchy. They're then compared to actual sensory input. And then the difference between the predictions and the actual input, the prediction errors, are then propagated back up the hierarchy. And this allows the predictions to then be refined, and then they're sent back down the hierarchy compared to sensory input, and then prediction errors sent back up again. And this whole process is a continuous iterative process analogous to message passing algorithms in hierarchical Bayesian models. This has really been a very hot area over the last 5 or 10 years. So I did a Google search on predictive coding in neuroscience. And we can see that, in 2016 and 17, a total of 10,000 papers on this subject. And these papers are either testing the theory of hierarchical predictive coding, they're taking existing imaging results and interpreting them in the light of this new theory, or they're helping us to understand various disease processes and come up with proposals for clinical intervention, or they could be more mathematical, people developing new message passing algorithms and proposing how they might map more specifically onto the neocortex, really digging into the details. Okay, so that's the end of my talk. I've got some take-home messages here. I'm just going to leave them up for you to read. I'll put them back in a second. I just wanted to say one more thing, which was that I'm sure you can understand that the source of research I've been talking about requires lots of people from different disciplines to work together. And we may not understand the terminology that each other uses. And so now there are a couple of new disciplines which hope to join the dots, if you like, and one of them, and they're called computational psychiatry or computational psychology. And in the autumn of this year, we've developed the first computational psychology undergraduate course in the UK. And this is a 3-year course that you can take. you'd come out of it as a British Psychological Society accredited psychologist. But along the way, thanks to colleagues in the computer science department, you will have learnt all about machine learning, computer programming, and mathematics in order to test ideas like hierarchical predictive coding, etc. So thank you very much for your attention, and thank you.
Okay, my name's Professor Kenny Coventry. I'm head of the School of Psychology, and I just want to say how thrilled we are to have Will join us in psychology here at UEA. But while your brains are still fresh, before I say a few other words, I'd just like to invite any questions. Are there any questions for Will? Question?
If I understood you right, Will, you said that you rather believed that the brain was a sort of Bayesian inference engine. But behavioural economists, time after time, show that people, when they make decisions, don't make them in a Bayesian way. So what's going on? It's Bayesian at the bottom, but not at the top?
Okay, so the brain's Bayesian at the bottom, but not at the top.
Yes, well, that's everything. Actually, that's an interesting observation, actually, because really what I've talked to you about today has been really sensory processing pathways and how they're integrated with things like memory and so forth. But I haven't talked about decision making. And there's a whole other computational modeling framework called reinforcement learning, which has made terrific inroads into our understanding of the decision-making circuitry in the brain. And indeed, DeepMind's success in solving problems like Go was achieved by marrying these two technologies together, deep learning and reinforcement learning, to create deep reinforcement learning. And so, now, you could do Bayesian inference correctly, but if you've got the wrong priors, then you're going to get a result that's not optimal. So that's actually a perspective on various clinical syndromes, for example. So people think maybe that the positive symptoms of schizophrenia are to do with people's priors being too strong. So rigid thinking. You know, you're not paying enough attention to the data that's coming through your senses. Your priors are too strong. I'm not sure I have a... interestingly, I'm working with Anders Poulsen from the Behavioral Economics Center on looking at some models of decision-making in sort of game theoretic contexts. Now, what game theory has is it assumes people know the sort of different payoffs for making their decisions. But in the real world, we don't know what these payoffs are or what the values of decisions are going to be until we've been exposed to an environment for a long period of time, until basically we learn the appropriate values. And that's the sort of approach that reinforcement learning takes. You're learning values, and then you make decisions based on those values. So, what do you think about that answer?
Well, am I allowed to say something? I
Yeah.
think what you're saying is it could still be Bayesian, but if you train it badly, your brain, it will come to the wrong decision. The priors are wrong.
Yeah, so if the priors are wrong, then if you've got very strong priors, that's going to, effectively, you're going to be ignoring the data, which is not a good thing.
You just explained Brexit. Well done.
Somebody had to mention Brexit. Somebody had to mention Brexit. Can we take another question? Time for maybe one final question. Gentleman in the middle. Okay, so the question is schizophrenia, or at least one variety of schizophrenia has to do with an overpowerful top-down prior.
Yeah, that's been proposed as as what might be happening for schizophrenics who really have positive symptoms, so hallucinations and delusions. So, you know, if I think I'm Mary Poppins, and no matter what Kenny says, I really think I am Mary Poppins, and regardless of what you say, so there's no sensory information is going to change that opinion. So that's really a delusion. So that's sort of a very strong prior. And people are starting to relate the strength of beliefs and learning rates in neural systems to different neurotransmitter systems, such as dopamine, serotonin, the cholinergic system, etc. And so certainly dopamine, for example, has been implicated in schizophrenia, and we're just really trying to unpick the relationships between, you know, the weight that you give to data versus the prior, and how different neurotransmitters actually encode that in the brain. Yeah.
Is schizophrenia nature or nurture, is the question.
I'm not an expert on schizophrenia, but I believe there is a hereditary component, so there's got to be a genetic factor here. But I'm no expert on schizophrenia.
Okay, I'd just like to say a final few words. And first of all, like to thank Will once again. I hope you'll join me in thanking Will for a fantastic talk. Thank you. And I think, Will, you've deserved some refreshment. So please, everybody, hope you'll join Will outside and we can continue questions outside. There are refreshments outside. Thank you so much for coming. Thank you again, Will.